All right, so we're going to prove that the cube of any integer can be written as the difference of two squares. And this is the hint Burton gives us. And this is easily verifiable. I think it's worth doing. So it's basically saying n cubed is equal to 1 cubed plus 2 cubed plus dot 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 plus n minus 1 cubed plus n cubed, and then minus 1 cubed plus 2 cubed plus dot 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 plus n minus 1 cubed. So as you can see, everything cancels. The n minus 1 cubed minus n minus 1 cubed, and you are literally left with n cubed. So let's go ahead and start the proof. The reason why he does this is he wants you to remember one of the previous theorems that were done as an exercise. So he's wanting to remind you from 1e, right? In his book, we had 1 cubed plus 2 cubed plus dot 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 plus n cubed is equal to n times n plus 1 over 2 squared. And this was true for natural numbers n bigger than or equal to 1. So we can't just flat out use this because they're saying any integer, right? But he wants us to use this as a motivation, right? So he wants us to, okay, consider. So we're looking at this. So let's say this is using this formula, right? Straight up, it's going to be n times n plus 1 over 2 squared. And then minus, right? So now it's 1 cubed plus 2 cubed plus dot 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 plus n minus 1 cubed minus, so it's the same thing but with n minus 1. N minus 1 times n minus 1 plus 1 over 2 squared. So he wants us to look at this from this, right? So basically, if we can show that this here, just using algebra, is equal to n cubed, then we've proven that n cubed, or any integer, can be written as the difference of two squares, because look, these are two squares, right? Okay, so let's go ahead and do that. So I can see this is going to be n squared, n plus 1 squared over 4 minus n minus 1 squared. And then this will be n squared over 4. So we can factor out an n squared. I can see that, n squared. And I'm left with n plus 1 squared minus n minus 1 squared over 4. And then I can see this difference of squares here, right? So this is going to be n squared times n plus 1 minus n minus 1 times n plus 1 plus n minus 1, right? That's our difference of squares. And this is over 4. Okay. So this is going to be n squared times, so this is going to be plus 1 minus 1, so n minus n, so this is negative, negative, positive, so this will be 2. And this is going to be n plus n, 2n, and then the 1's cancel, over 4. And then we have 4n cubed over 4, which is n cubed. And that's super cool. From just the motivation from this previous problem, we were able to come up with n cubed is equal to this difference of these two squares. And of course, we're able to justify that n cubed is in fact equal to the difference of these two squares from this motivation from a previous problem, which is really a really cool implementation in his book.